Hey everybody. In this final video from chapter 6, we're going to get complex. So how do we see more complicated things like the various colors we see out in the world, and then complex objects and movement of objects in space. So we're going to start with color, and color has long fascinated us. We've had whole industries built around trying to mix colors together to make beautiful fabrics and paintings. We have whole art projects dedicated to study of color and how we perceive color and how it makes us feel. It's a major part of our psychology is looking around the world and experiencing the different wavelengths of light differently, and then building society at least in part, um, around different colors to help us feel things and communicate things. So, how do we actually psychologically and biologically process those colors? Well, there's three primary theories for how we do this biopsychologically. And we're going to walk through each of them. There's the trichromatic theory. It was proposed by Jung and Helmholtz. This was one of the first theories, and then opponent process theory came just shortly after. Those two theories kind of battled it out for a while. We'll walk through each of them. And then finally, the Retinex theory came a bit later. Is going to kind of take a bit of a different perspective on color theory. As a note, as kind of um, a spoiler, when you think about theories, typically you think of theories competing with one another, where one of them must be correct and the other ones must be incorrect. Um, these are actually potentially complementary to one another, where um, each theory may be able to explain part of the color processing system, right? And they may each may contribute to a bigger explanation that involves multiple processes. So they might work together. Trichromatic theory is tri means three, right? And chroma means color. So essentially, trichromatic theory is the idea that there's three colors, three basic colors that we process, and that we have three kinds of cones to do this, right? If you remember in the retina, you've got rods and cones, and the rods process dark and shades of gray, whereas the cones are processing color. Well, the idea behind trichromatic theory is that there isn't just one kind of cone, there's three kinds of cones. And each of the cones are going to process different wavelengths of light. So some of the cones are going to be attuned to low wavelengths, right? Or sorry, fast wavelength, right? And then some cones are going to be attuned to slower wavelengths, right? And then some are going to be kind of in the middle. And it's not, you know, that they don't respond at all to different wavelengths, but they respond preferentially to certain wavelengths. Okay, so if light comes in at this wavelength down here, it's going to activate these cones mostly, these cones just a little bit, and these cones not at all. Make sense? This was actually demonstrated before we were able to really get into the retina and study the cones and how they individually work biologically. And it was inferred based on color mixing and matching. Because we learned over time that you can mix and match colors to make new colors. And in fact, you could make the whole spectrum of colors by just mixing three colors that were just far enough away from each other along the wavelength, right? You might know our primary colors, red, green, and blue. You can mix red, green, and blue in different combinations and get basically anything along the spectrum. Your printers, a printer can print any color with a combination of cyan, yellow, and magenta. You'll see cyans, somewhere in this range, yellow's up here, magenta's up here, and you'll see that those are really going to differentiate. Magenta's only going to activate these, right? Yellow's going to do a combination of these, and cyan's going to do a combination of these. So we're differentiating as we go. We later demonstrated this physiologically. So this theory that we must have three processors because we can mix three colors turns out to be accurate when you actually measure the cones themselves. you expose them to light. You isolate the cones, you expose them to different kinds of light, and they do actually absorb light at different rates depending on the wavelengths. So that's evidence for trichromatic theory. So we got it solved, right? Colors are processed by the cones. There's 3 different kinds of cones. We mix that up, we get all the colors. And this also can account for color vision deficiency, where people with color vision deficiency don't typically see no color at all. What they'll do is they'll have difficulty differentiating certain colors that can be accounted for by a certain cone not developing properly. So a common type of color vision deficiency is red-green color blindness, where people have difficulty differentiating these red dots from the green dots because they're high wavelength, slow wavelength cone doesn't develop properly, so there isn't a cone to differentiate those colors at the top of the spectrum. Right? So differentiating this 57 here, maybe you can see this, right, from the surround is difficult. It's difficult differentiating this 8 from the surround is also difficult. Okay, so we've got trichromatic theory based on mixing colors, mixing cones, right, and accounting for lots of color vision deficiencies. But this isn't the only theory. Another theory came out called opponent process theory. And this was based on the observation at first that some combinations of colors are perceived and interpreted as combinations, and some combinations of colors really aren't perceived as a combination of the 2 colors. They'll be perceived differently, right? So bluish green, we can describe that, we can look at it, we can say, yeah, this is about halfway between blue and green. I can see the blue, I can see the green, it's about halfway between. No problem. Whereas there are certain colors like reddish green that are sometimes referred to as impossible colors. So this is sort of halfway between red and green, but we perceive it as brown instead. We don't see the green in here. We don't see the red in here. We've got a new name for it, brown. Same thing with bluish yellow. This doesn't look bluish yellow. It kind of looks like a dirty green, doesn't it? So some combinations can be perceived as like a middle point, like it's being put together, and some combinations are seen not as a combination, they get interpreted differently. So the theory was that we've got these sort of polar responses where you might have cells in your brain that are either doing the positive response or the negative response to these complementary colors, right? And the complementary colors are like red and green, blue and yellow, and then we've got bright versus dark as opposites. And later, we described that this happens not in the retina itself, but beyond the retina. So beginning at the bipolar cells, bipolar, right? And then later on into the thalamus and into the occipital lobe. There's some evidence for opponent process theory as well in the case of after images. So here's an image that will provide an after image if you stare at it just long enough. So go ahead and look at the center of this image. I'll take my laser pointer away in just 1 second. Just look at the dot for about 10 seconds. And you should see, after the dot goes away, you should see an after image of a red, white, and blue flag. And you can try this on your own if it didn't work for you in the video, but you should see that after image. The idea is that green opposes red, and so if you stare at green for a while and then the green goes away, the cells will tip to their other pole. So we've been like pressing them into the green for a while, and then you turn that off and it'll wobble back essentially to its opposite process, which is red. Okay. Now, it turns out our cells really do this. Okay, so we've got cells that will respond in one way to red and then the opposite way to green, and the after images are evidence of that. The final theory for color processing is called the Retinex theory. So far, we've been at the mercy of our retinas and the light that hits them, but we don't actually depend just on the light from the outside world. We perceive the world and its colors in a more complicated way. And one of the more complicated ways we perceive the world is through color constancy, where the same color can be seen in different wavelengths of light. So if I have a yellow banana in a brightly colored room and I take it to a dark room, I'll still see it as yellow. If I take it into a red room, I'll still see it as yellow, right? And because it's a banana, right? I'm never going to see it as a red banana or a green banana or a bluish banana. I'll know that it's a banana and I'll process it as yellow. I'll see it just as yellow, even in a different room. There are a number of demonstrations of color constancy, and the critical role that the context plays, the light that surrounds what it is that you're seeing, can change the way that we see the colors. So here's strawberries on a plate that are going to look red to you, um, but the color on this image is actually not red. You'll see it's this like grayish color, but we perceive it as red because the surrounding color is all sort of washed out in this blue color, and we'll see it in context and process it as red, partly because we know that strawberries are red. You'll see here, based on a difference between a red surround and a green surround, we're going to look at these colors on these Rubik's Cubes a bit differently. This one over here is going to look like a light blue, and this one's going to look kind of like a dirty red. But if you actually compare them to one another, you'll see that they're both kind of in the middle. Here in this kind of orangish brown color, but we see that as red up here in comparison to green, and we see it as blue down here in comparison to red. Final demonstration, you might have seen back in the day a dress that looked like this. Some people will look at this dress and they'll see it as black and blue, and some people see it as more gold and white, like this. And what we're doing is we're looking at this dress here, and we're thinking about it in context. Okay? So is this a black and blue dress under certain lighting conditions, right? Or is this a gold and white dress in certain lighting conditions? And we adjust based on context. So Retinex theory was developed in part to account for this kind of thing like color constancy, right? And the general idea is that the color of your object is determined by the relative reflectance. Okay, so it's the light that we're seeing, not purely based on what hits our retina, but relative to the surrounding objects in context. Okay? And it turns out that there's evidence for this in your brain as well. So in your occipital lobe, not in your retina, right? Retinex, beyond the retina, we've got these dual opponent cells actually analyze the contrast between wavelengths. Okay, so what they're going to do is not just process the wavelength for red, but they're going to process the difference between the red and the green in the area around. And so they're going to process red relative to other wavelengths around it. That way you can always see a banana as yellow because you're going to be comparing it to the things around. That's Retinex theory.